Now, if you look over here on the left-hand navigation bar, you'll notice that there's solutions, and I've actually included the code for all of the different activities that make up this, and so you can kind of go over here. And so I'm going to cheat for this and just go straight to the solution for this third exercise set, but kind of walk you through how to go about it. And so what I've done, we're now looking at the Earth going around, the moon going around the Earth. And all I did was I took this code here, I copied it, and then pasted it down here, and then went ahead and made some tweaks. Everywhere I had Earth, I changed that to moon. Everywhere I had sun, I changed that to Earth. The year is no longer the relevant time scale, but the month is. The other thing is I had to decrease the time step size. If I used 1 times 10 to the 4 seconds for each time step, because we're dealing on a much smaller scale, you run into issues. So what we're doing here now is trying to match up the apogee and the perigee of the moon. And so we start off with the moon at, say, the apogee. You could just easily start with the perigee. And then I'm going to give the moon some initial speed that we'll have to tweak. And this should give me the velocity needed for a circular orbit. Now, the other change I've made is I now need to keep track of the closest and the farthest distance between the Earth and the moon. And so what I've done is I've added in some if statements that are going to check these different properties. So the thing to notice here is we start off this statement with if, and then here we have a condition that it's going to check whether this is true or false. And so what this is looking at is the magnitude of the moon's position and whether or not that's greater than some value. I initially set that equal to 0. The other thing to notice about the if statement is that the line ends in a colon. And then if you hit enter from here, this will be indented by 4 spaces or 1 tab. And so anything that is indented is now part of that if statement and will be carried out when this condition is true. So if the position is greater than some value, it now sets that simulated apogee to the current position. And this will check every single time it goes through this while loop. Do something similar with the perigee. The only difference is we can't initialize the perigee to 0. We set it to some value that we know should be a maximum. And then it's going to check, and if the current position is less than my simulated perigee, then it updates that. And so if I go ahead and run this, we get a nice orbit around the Earth. And now let's take a look at these values. So the apogee of 6 times 10 to the 8 and a perigee of 4 times 10 to the 8. So those are way too big. So what I'm going to do is set my initial speed to some fraction of what I set it to. And a useful skill to instill in your students is this notion of making educated guesses as to the results and tweaking them and just running them. Think of this as like a virtual experiment. And so let's try 75% of the initial speed and see how that works. And so if we run this, here's my initial speed. That's definitely looking a little bit more eccentric. All right, so apogee. The apogee matches up with what we'd expect. However, the perigee is too small. So we need to speed this up a little bit. Let's try let's try 0.85. All right, so that's a little closer. Let's see. Let's do. Let's try 0.885. Split the difference. And that's actually not too bad. We're going just a little too fast. So let's try that right there. And I can continue to tweak this value to get closer and closer. So you might want to go play around with that and see what you can, how close you can get.